Hello, I'm Vincent Rooyakkers, and this is Lab 2, Motion of a Falling Object. In this lab, we were tasked to observe the motion of a falling object that falls slower than a rock. We would then compare our observations with computer models of this motion with and without drag. With this, there was a focus on Newton's second law, namely that an object's acceleration can be derived from the sum of forces acting on the object. By applying this to the motion of an object, we can also tell when and what an object's terminal velocity is, as this is the speed which is the fastest an object falls and is constant. Therefore, there is no acceleration acting on the object, and thus the sum of the forces must be zero. In my lab, I used a crumpled paper ball which has an assumed weight of 0.0045 grams and dropped it from my height. For my tracker analysis, I set the origin to be the ground, so in my data, at a set time, positional data closer to zero shows that the object fell a lot faster. Here is my tracker footage. Using my tracker data, I began with the model without drag. For the initial conditions, it's just the ball's mass, which was previously explained. The initial position is my height plus the length of my arm, as determined by tracker. So going into the calculations, we see that net force is essentially just the weight force, as we're not using drag yet. And weight force is just ball's mass times the acceleration due to gravity times the negative directional unit vector, as this is because the weight force is pulling the ball down. Going into the calculations, it was important to use a small delta t because we want the ball's velocity to change as little as possible so that the ball's position updating equation is as accurate as possible. So now let's watch this model run. Okay. So moving on to the model with drag, there's a few key differences as we now have the proportionality constant, which is used in the calculation of drag force, as we're now using drag force. So looking at net force, it's now the weight force added with the drag force, and since the drag force always moves in the opposite direction that the ball's moving, the primary force being the weight force pulling it down, so we're no longer multiplying the j hat by -1. So we see that the force of the drag is j hat times proportionality constant times the magnitude of the ball's velocity squared. This is just how we calculate drag force. So now let's watch this model run. One key thing to notice with this model is that you can't see the force arrow for drag force, and that's due to having such a low proportionality constant, as drag force for my observation and with this model is such a minor factor that it's hard to see, but it's there. Looking at the graph of the results, we see that the two models fell at roughly the same speed, and that my observations fell the fastest. This may be due to having to approximate the mass of the paper ball by using a standard weight, as I did not own a scale or have access to one. Therefore, I will analyze the endpoints for my data. Looking at this data, the model without drag fell the furthest, while the model with drag fell the least distance. This is due to the estimation used to get my proportionality constant, but this data falls into what was expected. Due to constantly accelerating due to having a net force not equal to zero, the one without drag should have fell more as the ball was constantly speeding up. This was not the case for my observations or my model with drag, as there was a drag force counteracting the force of gravity. Although the net force was never zero for this case, or my observations, acceleration did gradually decrease, resulting in falling less distance. Going into the questions we were asked to answer, the model that involved drag would eventually predict terminal velocity if given enough time, as the drag force would gradually become large enough to counteract the force of gravity completely, resulting in falling at a constant speed. On the other hand, the model without drag would just continue to gradually go faster and faster. If the object was initially thrown down, terminal velocity would not change, as terminal velocity is the case, in this case, is the point where drag force equals the force of gravity, and this throw only changes the initial kinematics of this, with in this case the initial velocity. For a greater terminal velocity, there would be a greater weight force, which would involve the object's mass or the acceleration due to gravity. Thanks for watching.